So I'm going to share my screen. So I hope you can see my screen.
Yes, sir.
Okay, thank you. So today Dr. Udesh will not be available. So I will continue the lecture. So last week you have started to study the sampling, no? The new topic sampling. Okay, so this sampling is a very important topic. Okay, actually this is we can say this is the most challengeable signal processing techniques uh, today, and it is still developing. Okay, so this sampling is very important, and in practical system we have to use sampling in many places, especially in A to D conversion, sometime at the signal detection, so on. Okay, so these sampling techniques are used regularly in a practical system. So this topic is very important. Okay, so I think Dr. Udesh in previous session, Dr. Udesh has mentioned some fact. Okay, so I will have a quick recap. Okay, so he discussed about continuous signal and discrete signal. No? Continuous signal and discrete signal. Okay, discrete signal. So so actually we have learned these continuous signals and discrete signal, about continuous signal and discrete signal in classification of signals. So we have a little idea about these two type of signals. Okay, so you know that continuous time means the time values are continuous. Okay, and discrete means the time values are discrete. You have limited countable value, time value here. Okay, here you have continuous value, that means you can't count. Okay, here you have uncountable values, uncountable time values. Okay, here you have countable time values, countable time values. Okay. So if we talk about sinusoidal signal, we have continuous time sinusoidal signal as well as discrete time sinusoidal signals. Okay, so so we can denote it as like this: xt equal a cos 25. I will put capital F here. Okay, because Dr. Udesh used capital letters here to denote the continuous time signal frequency plus theta. Okay, so this is a continuous time sinusoidal signal. So you know this signal will be look like this, no? This will be look like this. Okay, so here you have A and here you have minus A. Okay, and you have some t values. Okay, so this is t and this is xt. Okay, so discrete time signal you can represent as xn. Okay, xn. Okay. So this n is a sequence. Okay, it is a number. Okay, normally this n is from 0 to plus or minus 1, plus or minus 2, up to infinity. Okay, that means this n normally lie between minus infinity and plus infinity. Okay, so we can represent this discrete signal, discrete sinusoidal signal as a cos 25f. Here I will put simple f to denote the discrete frequency fn. Here instead of t, we have to put n. Okay, so this signal is with respect to n. Okay, not with respect to t. Plus theta. Okay, so this is the continuous time signal. Okay, and there you have learned that so this signal will look like this. Okay, look like this. So here you have n variable. Okay, so this variable have some finite value, 1 2 3 4 5 like this. Okay, and also it have minus value also, -1 -2 like this, and here is the 0. Okay, and you will get this kind of one. Okay, this kind of signal, this kind of samples. Okay, this kind of so discrete value signal is this kind of signal. Okay, so you can see that here in time you have every values. Okay, every values there, but here you have some distinguishable value. No? Here 0 1 2 3 4 like that. The between values are not there. Okay, so value between that's 2 and 1 is not available, only 2 and 1 available. Okay, so that is the idea of the discrete value signal. Okay, and also you have learned that here you can put this is 25f as omega. Okay, so that is angular velocity. Okay, so I will use capital omega to represent this angular velocity or angular frequency. It is equal to 25f, capital F. Okay, so this is angular frequency or angular velocity, and this is the normal frequency. Okay, so normally this measure cycle per second. This refer radian per second. No? Radian per second. Okay, so how much angle will go within 1 second? That is the idea of the angular frequency. And normal frequency, how much cycle per 1 second? Okay, that is the idea of normal frequency. Okay, both are linearly these two have linear relationship. Okay, so you can use f or omega at any time. Okay, so in discrete time signal, okay, so we will use simple omega to denote the omega here, and it is equal to 25f. Okay, 25f, and 25f. Okay, and you know, this is the sinusoidal signals are normally repetitive signals. No, these are periodic signal. Okay, so these are periodic signal. For example, this time t, this time duration. Okay, if this is a cos signal, this time duration we consider as the fundamental frequency. That is the repetition period. Okay, this t. Okay, Dr. Udesh has explained this, so I'm not going to take much time to explain this. Okay, so in continuous signals, continuous sinusoidal signal, repetitive signal, you have fundamental period. Okay, fundamental period T. Okay, so this is normally measured in second. Okay, so normally this is a time duration. Okay, so normally measured in second, this T. Okay, that is the fundamental period. Okay. Okay, so and there is a connection between the fundamental frequency and this fundamental period and this frequency. Okay, so you know that this fundamental period T means, okay, that is the time to to get one circle, no? That is time that takes to get one circle. Okay. That is the fundamental period. So here this is one cycle. Okay, so this is one cycle, and this T is equal to one cycle duration. No? So this duration is per one cycle. Okay, so at T, one cycle. Okay, so so if we want to find the time for this one cycle, for if you want to find how many cycle per 1 second, so simply you have to divide this by T, and this also you have to divide by T. Okay, so this is T, this T, time T for one circle. So 1 second, so this is second. Okay, so 1 second, it will take 1 by T cycle. Okay, so 1 by T cycle for 1 second. So that is the frequency. That is the F. Okay, so we can also say that, okay, this F is equal to 1 by T. Okay, T is the period of the signal. Okay, so omega, we can also write like this, omega 2 phi by T, and it is also equal to 2 phi F. Okay, so we can write this. Okay, so we already know this. Okay. In case of discrete time signal, okay, in case of discrete time signal, uh, this is a sinusoidal discrete time signal. Okay, so this also repeating, this signal also repeating. Okay, after some time you will get the same sample. Okay, so this sample, the same sample, same value will you will get after some time. Okay, then that time that duration we called as a period. Okay, but here it is the number of sample. Okay, so here in case of a discrete time signal period, we denote it as n. Okay, so this is the period of discrete time signal. So we denote it as n. Okay, here for continuous time we denote it as t. Okay, so it is the t is measured in second. Okay, but here n is a certain number of sample. Okay, so here n is certain number of sample. So this is a number of sample. Okay, so we denote that this n. It is not second, it is a number of sample, some sample. Okay, after 5 sample you will get the same sample. Okay, so that n is 5 at that time, n is 5, for example. Okay, so this is n is a certain number of sample. Okay, it is not measured in time, it is a number of sample. Okay, so so this is number of sample n. Okay, so if you get, okay, so So here, so this is a number of sample in one cycle, no? Okay, I'm sorry, here is the highly thundering. That is why I stopped. Okay, let's continue. Okay, so here, so you know that this is n, that is the number of sample. Okay, so what is this number of sample? This number of sample, okay, in one cycle, no? Okay, so I will draw it here. Okay, so if I draw a sinusoidal signal like this, okay, like this, okay, so you can see that after this sample, say this is this sample 1, 2, 3. I just get the example. Okay, so approximate value I will get. So I have 1, 2, 3, 4, 5, 6, 7, 8 sample. Okay, so after this sample, this 8 sample, again we will get here. Okay, and this after the 9 sample will be this one. Okay, so after 8 sample, we will get the same sample here. No, after 8, we will get the same sample. Okay, so this is 1, and this is the 9th sample. This is the first second sample, and this is the first sample, 9th. So let's say this is a 0 sample. This is the first sample. So 0 sample, you will get at 8th also. No, 8 sample and 0 sample is same. And first sample and 9th sample is same. Second sample and 10th sample also will be same. Okay, so you can see that this n is a certain number of sample. Okay, this n is a certain number of sample. Okay, and that is the sample in one cycle. No, so this n is number of sample in one cycle. Correct? Okay, this n is number of sample in one cycle. Here t is the time of one cycle. This t is a time of one cycle. But here n is a number of sample in one cycle. So here n is a number of sample in one cycle. Okay, so if we want to find how many so how I take it, how I tell you. So if you want to find how many cycle, okay, how many cycle in one sample, okay, here you find how many cycle in 1 second. Okay, now you want to find how many cycle in one sample. For that, here n sample you have in one cycle, then to make this 1, you have to divide it by 1, and this is this 1 also you should divide it by n. No? So this is one sample with this cycle. Okay, so this is cycle per sample. No, sample per cycle. No, cycle per one sample. No, is it correct? Here this is number of sample. I think you can understand it. Okay, a number of sample in one cycle. Okay, here number of cycle, here 1 by n is number of cycle. This one, this value is number of cycle in one sample. No, correct? Okay, so that is the frequency of the discrete sine signal. Okay, so here cycle in 1 second, that is the frequency of continuous time signal. Okay, number of cycle in 1 second. That is the frequency of continuous time signal. And for discrete time signal, that is number of cycle in one sample. Okay, that is number of cycle in one sample. Okay, that is the frequency of the discrete time signal. Okay, so in discrete time signal, you can write frequency as 1 by n. Okay, and also you can write this omega is equal to 2πf. So you can write it as 2π by capital N. Okay, so so this is the relationship with omega, angular velocity or angular frequency, and phi, normal frequency, and with n. Okay, sample per one cycle. Okay, in case of discrete time signal, you have capital omega, 2π capital F, 2π capital T. This is time per one sample. Okay, correct? Okay, so these things Dr. Udesh also have explained very well. So I hope you get it. Okay. And if we again, if I remind you the unit of this parameters, this omega is radian per second. Okay, this f is per second. Okay, and this t is in second. Okay, this is radian per second. This f is per second. That is hertz. Okay, it is per second, no? 1 by s. This is the hertz, and this t is normally measured in second. Okay, in time. It is a time duration, second. Okay, so can anyone tell what is the unit of this omega in discrete time signal? Can anyone tell? So I think you know this. What is the unit? Is it radian per second? Can anyone tell? Is it radian per second? Yes or no? Is it radian per second? So I would like if you can talk with me. Okay. It is okay if the answer is wrong, that is okay. Okay. So is it radian per second or anyone? Radian per second. This omega is radian per second. This f is per second. No, that is wrong. Okay. So I think you know the answer, but you don't. I think you are shy to answer, no? Okay. So this is not radian per second actually. This omega is radian per what is sample, because this f is not time per one sample. It is sample per one cycle, sample per one cycle. So this is number of sample per sample. This is per sample. So here you will get radian per, not radian per second, you will get radian per sample. Okay, radian per sample. And this 5 you will get, it is not per second, it is per sample. This is F is per sample. Okay, and this N is samples. Okay, so that is the unit of the discrete time signal parameters. Okay, so I think you got it. Okay, and Dr. Udesh also mentioned that. Okay, Dr. Udesh also mentioned that this one, it is related to discrete time signal only. Okay, so I think you should know these things. Okay, so again, try to memorize these things. This is a continuous signal, this is a discrete signal, and this is how continuous signal look like, and this is how discrete signal look like. Okay, and this is the relationship between the angular velocity and the frequency and period of a continuous signal. Okay, omega 2 phi f is this. Okay, omega is equal to 2 phi by t, and it is equal to 2 phi f. So this relationship you should have keep in your mind. Okay, and you should know this unit of this parameters, this omega, t, and f. So this t is second. So this omega will be radian per second, and f will be per second, hertz. Okay. So in case of discrete time signal, okay, in case of discrete time signal, so this is the relationship between the angular velocity frequency, and here 2 phi by n. N is not there. 2 phi by n. No? Okay, so this is the omega is equal to 2 phi f and 2 phi by n. Okay, so this omega is number. So this n is number of sample. Number of sample. It is not time. Okay, number of sample. So this f is sample per one cycle. Okay, sample per one cycle. That means per sample. You will get it per sample. And here, here omega is radian per sample. Okay, so this omega is in radian per sample. So you have to keep in your mind these parameters. Okay, so that is very important. Okay, so another thing you have learned there, that is, if you get sinusoidal signal, let's say called signal. So let's say omega naught n. So this is a discrete signal. Okay, and also you have you can have a phase shift. Okay, and it is equal to cos omega naught plus 2 phi k n plus theta. Okay, so this also you have learned. No? This one also you have learned. So this also you should keep remember in your mind. Okay, so so let's see what is the condition. There is a condition to satisfy this identity. Okay, So we will see that condition. Okay, I will show it in MATLAB. Okay, so try to memorize this. Okay, so you have learned that cos omega naught n plus some value plus, plus some phase shift is equal to cos omega naught 25 kn. Okay, so this is the new angular frequency. We can say it as omega k. Okay, so here omega k is equal to omega naught plus 25k, and this k can be 0 to, okay, this k is an integer value, and it can be minus infinity to plus infinity, no, but integer 0, 1, 2, 3, minus 1, minus 2, likewise. Okay, so let's see how this happens. Okay, so I think in mathematical way, you can, in mathematically, Dr. Udesh has shown that this one and this one is equal. Okay, so can anyone tell what is the condition to satisfy this? What is the condition? There is a special condition of this n. What is that condition? What is the value of this n should be to satisfy this condition? That is very important one. Can anyone tell? If anyone if anyone try to draw this in MATLAB or in by hand, I think you should get it. Okay, there is a condition for this n. What is that? Okay, so I will get example. Okay, I will get example to give you idea. Okay, so I will get omega naught as 5 by 2. Okay, so this is example. Okay, so I get omega naught is equal to 5 by 2. Okay, omega naught is equal to 5 by 2. Okay. So so if we draw this signal, okay, if we draw this signal, so I will take as x1 t, okay, x1n. Okay, so I will have cos t omega naught is 5 by 2 and n. Okay, so if I write this signal, okay, write signal, I will write in on the MATLAB. Okay, it is easy. Okay, so here this is the signal. Okay, okay, so here this is the signal x1. It is cos 5 by 2. Here you can remove the 1. Okay, you can remove the 1. I will remove it. Okay, so here 5 by 2 n. Okay, so that is the same signal. No? This signal cos 5 by 2 n. Okay, so 5 by 2 n. Okay, if I plot that signal, okay, if I plot that signal, what happened? Okay, if I plot that signal, okay, so now I'm going to plot. So I have defined n from 0 to 0 0.01 from 6 up to 6. Okay, so here I get, okay, for my example, I get this n. To plot the graph, I get this n value from 0, 0 0.001, 0 0.002, likewise up to 1, then 1.001, likewise up to 2, then up to 3, and up to 6. Okay, so I get this n from 0 to 6 with 0.001 increment. Okay, correct. Okay, so I think you know now MATLAB. Now you know the MATLAB. You know MATLAB. We have done it in first signal and system one. That is why I use the MATLAB plotting. Okay, so here I have defined the n. Okay, so now I'm going to plot it. So how it plot? Okay, so what MATLAB simply do? The MATLAB, so you have n values. Okay, 0, 0 0.001, 0 0.002, likewise up to 6. Okay, then you will get first x, the MATLAB will count the x value. Okay, so he put 0 to here and get that value here. Okay, then he put 0, 1, 0, 0.001 here, then he count this value, then put it here. Okay, and again 0.002, he put it here, substitute it here, and find the x13 value, then he will put it here. Okay, likewise he just made two arrays. No, he define one array for n and one array for this x1 value. Okay, when we give the plot command, okay, when we give the plot command, plot x1 with respect to n, then he plot it. Okay, then what he do? Okay, he divide this n axis to 0, 0 0.001, 0 0.002, 0 0.003, 0 0.004, likewise. Then he put this value, the calculated value. From 0, he will get 0. From 001, he will get some value. From 002, he will get some value. Likewise, he mark those value. When we give the plot command, he just join these points. Okay, then plot the graph. Okay, so we will see what happened. So you can see that we have plot. Okay, so we have plotted as a continuous signal. Okay, if you want to plot it as a discrete signal, okay, so you no need to. So anyway, MATLAB draw the MATLAB can in MATLAB. I already told you this thing. Okay, in MATLAB we can't define continuous variable. In MATLAB we can't define continuous variable. We can define only discrete variable. Okay, but if you get a very close point, okay, very close point, okay, if these discrete values are very close in each other, then you will see it as a continuous variable. Okay, that is how MATLAB plot. Okay, so originally MATLAB take continuous value. Okay, sorry, discrete value. So here also it takes discrete value. You can see that for this n, you can see these are discrete value, no 0. This is another value. This is another value. Likewise. Okay, so these are discrete value. Okay. So if we get this very close point, it will look as a continuous variable, but it is not really a continuous variable. Okay, so don't confuse. Okay, don't get confused. Don't be confused. Okay, so if you want to plot the discrete signal, here you can use the command is stem. That is how I don't know how it pronounce. Okay, I pronounce is that stem. Okay, so I use stem command. Okay, instead of plot command, then you will get only samples. Okay, only the discrete value. Second. Yeah. The problem is that we get very close sample. Okay, here we get very close sample. Here 0, 0, 1, 0, 0, 2. Here we get a very close sample. So you can't see separately these samples, this discrete value. Okay, so that is why you will get you get this kind of signal. So so anyone can suggest what to do to see the sampled version? Anyone can suggest what to do? I think you should have this knowledge now. If it is wrong, no problem. Okay, you can ask. So you can simply uh, reduce the, you can simply extend the point, no? So I will get it points 0.1. Okay. So I just so at that time I have get very close point 0, 0, 0, 1, 0, 0, 0, 2, 0, 0, 0.003, likewise very close point. Okay. First time I use 0, 0.001, 0.002. These are very close. Okay. So he calculate and when he plot it like this, okay, all these are, we can't separate these two. We can't see a separation between these 2 points. Okay. So I just simply extend the point. Okay, I get 0 and 0, 1, 0, 2, 0, 3, likewise. Okay, so I should see. No, now I should be able to see. Let's see. Can you see? Yeah, now you can see, no? And you can see the sampled signal like this. Okay. So this is so this is the sample signal. So sample signal is look like this, but I'm not going to draw the sample signal. Okay, I will draw the continuous signal. Okay, so I will use the plot here. Okay, so this is the signal we get. Okay, so now, okay, now so I think you can understand. Now we get omega naught as 5/2. Okay, so we have plot 5/2 in signal. Okay, so now we draw the continuous signal. Okay, we draw the continuous signal. We draw the continuous signal. Now we take another frequency. Another frequency. Let's get omega k is equal to omega naught by 2.5k. Okay, so I will get this k as 1. This k as 1. Okay, so I will get another frequency omega 1 as omega naught is here is 5/2 plus 2.5. So I will get 4 5/2. So I will get another frequency. Okay. So now I am going to plot the second signal. Now the frequencies, here the frequency is 5/2. This is angular frequency, but I normally refer it as frequency. Okay, that is okay, correct? Because these two are linearly. I told you just now, these two are linearly related. So we can use any parameters, omega or f. Okay, so here I use omega. Okay, so now I have some high frequency. Okay, so if that frequency is like this, low frequency, in high frequency means one cycle, he complete one cycle within less time. No, here this is the time for the low frequency. This is the cycle for low frequency signal, and high frequency signal, it will have several cycles here. No, that is because the frequency is high. Okay, so I will plot that signal also. You can see that we get several cycles there. So here I use this x2. Okay, this x2. Here it should be 5. No? Okay, 5 by 2 by n. So this is the second signal. Now I'm going to plot the second signal also in the same plot. Okay, hold on, and I plot it again. Okay, so let's see what happened. Yeah, so you can see that we get this one. Okay, so you can see it, no? So this is the red one is the low frequency signal, correct? Red one is the low frequency signal. This one, 5 by 2. Okay, 5 by 2. Okay, and next to the blue one is the high frequency signal, and frequency is 5 times higher, no? So there should be 5 circle in one here. One circle, inside one circle, this signal should be 5 circle there, no? Okay, so let's see. So you can see here one circle is here, no? This is one circle. Okay, so let's see how many circles there. One, this is the high frequency, this is one circle, one. This is another circle, 2, 3, 4, 5. Okay, so you can see that this red signal is low frequency, 5 by 2. The frequency is 5 by 2. And this blue signal is the high frequency signal. That is 5 times 5 by 2. That means this frequency is 5 times, the blue signal frequency is 5 times higher than the red signal frequency. Okay, so to complete one cycle to this red signal, okay, within that time, that is the period of this red signal, and with that time this blue signal will complete 5 circle, 5 cycle. Okay, so these are very toy things. Okay, basic things. Okay, actually now I should not tell these things to you. Okay, but I just want to give you an idea. Okay, so try to understand it with yourself. Okay, so here you have 5 cycles. Okay, so can you notice one thing here? Okay, so I will get, so you can see there are different value, no? Different value. There is no same value. Different value there. So if we get this point, Okay, here red circle has this value, value, and blue circle has this value. Okay, I can't write it, I can't draw, but I think, I hope you can understand it. Okay, so here different value, and here also different value. Here another value, and here it is 0. Okay, but here look at this point. Wait for a moment. Please give me a moment, okay? My kids has come. Give me a moment. Okay. 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 Sorry. Okay. I'm sorry. Okay. My kid is disturbing. So I think you got this. Okay. So this is a low frequency signal. This is high frequency signal, and you can see that there are the definitely the signal. You have two signal, no? This is a red one is a low frequency signal, and this one is a high frequency signal. And if you get the discrete version, you will get the same. Okay. If you get the discrete, so here I stem and stem. So here also you will get okay. So you can see that here the red color is the low frequency signal and blue color is the high frequency signal, and you can see that there is a two signal, no? Okay, there is a two signal. Here it complete one cycle from here. Okay, but here you can see that blue cycle will complete, blue signal will complete 5 cycle. Okay, 1, 2, 3, 4, 5. 5 signals there. Okay, so you can see that this is completely different signal, no? These two are completely different signal. So you can notice it. Okay. So again, I will put plot here. Okay. Because with plot, you can get it easy. Better than that discrete one. Okay. So here again, I just draw the continuous signal. Okay. So you can see that. Okay. But so you can see that if we get the discrete version also, there are two completely different signals. Okay. Then why, how can we say that? Then how can we say that this signal, this cos 5/2n is equal to cos 5/2n? Okay. How can we say this is completely wrong, no? So you can see that this signal is not This discrete version signal is not look like this discrete signal. Definitely you will get different signals there. Okay. But we are given that, okay, this signal should be same. Okay. So that is what I want to tell you. Okay. So in this condition, he said that this signal and this signal should be same. Okay, but we get the example and it is will not change. So if it is here, I didn't consider this theta. Okay, here for my example, I didn't consider this theta. I get this theta as 0. Okay, okay, but it is not same. Okay, but so what? So what is the reason? Okay, so C at 1. Okay, so C at 1. So you can see that this signal and this signal, you will get same value here. Okay, so C at 2. This blue signal also 0 and this red signal also 0. And C at 3. Okay, here, this point. And this point, it is about 0. No? It is about 0. Sometime more than, very little more than 0. Okay. Can we get some? Okay, no need. Okay, so at 3 you will get same value, and 4 you will get same value, at 5 you will get same value, at 6 you will get same value for this 2 signal. Okay, so if you get this n, okay, if you get this n as 0, 1, 2, 3, 4 integer. So this may be -1, -2, -3, -4 also. Okay, so integer. At that time, this point and this points are same, no? Okay, so at that time, cos 5/2 n and cos 5/2 n are same. Okay. See, okay, so you can see at 1 it is same value, 2 same value, 3 same value, 4 same value, 5 same value, 6 same value. Okay, so if we consider the n as, so here in our example, okay, we consider this n value from 0 to 0 0.001, 0 0.02 up to 6. Okay, but if you consider this the integer value of this n, that is 0, 1, 2, 3, 4, 5, this condition will satisfy. No, so note that this condition satisfy only this n is integer value. Okay, in sampling we will get this. Okay, in sampling we have to use this property. Okay, that is why you have to learn it here. Okay, so you have to get the idea that if this n is an integer value, 1, 2, 3 up to infinity, plus or minus infinity, okay, from 0, -1, -2, -1, -3, -1, -3, minus +3 likewise, okay, up to minus and plus infinity. If this n is an integer value, this condition will satisfy, not for all n value. Okay, okay, so that is the things you should get. Okay, so we will see. Okay, so if I consider this n, now I consider only integer value 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, then if I plot, okay, if I plot the continuous signal, okay, So you can see that here you can see only one signal. Okay, that means the other signal is inside here. So you will get the same signal here. Okay. Okay. So I will. So if I plot it in as a discrete signal, then is 10. Okay. So here you can you have some values. Okay, but these values are this red value, the blue values are first after blue signal is drawn. Okay, so first red values are drawn. Okay, then these blue values are drawn. So inside the blue value there should be the red value, but you can't see it because it is covered by this blue value. So I will plot it separately. Okay, so if you get this x1, so you will get this value x for x1. Okay, and if you get x2, so you will get the same value, 1 0.016, and x2 also. Sorry. 2. So here 5 by 2, it is to 5 for wait. Five by 2. So I get 5 by 2 and plus 2 5. That means for 5 by 2. That is correct. Okay. So here I draw the x1 2, and this should be same value. What's happened here? 1, 2, 3. So here I have 1. Here you have 1 3. This is the condition, no? 25K, no? This is the condition, no? 25K. Correct? Plus 25K. So I will get K as 1. Okay. So can anyone see my mistake? I have done a mistake here. Now I can't verify what is that one. Okay. 1, 2, 3, 4, 5, 6. It should be same value here. 5/2 plus 5. Let's take give me a moment. So let's see the condition. Okay, no condition is okay. Omega naught to 5. Okay, so K is 2K5. X1 0, 1 to 6. Okay, anyway, this one and this value should be same. Okay, this one, but here it is get different value. So I will check later what it happened. Okay, now I couldn't figure out it. When I try it in MATLAB, I will get the same result, the correct result. But now I think some problem is there. Okay, I couldn't verify what is the problem. Okay, anyway, I will find it and let you know it. Okay, so get the idea. Okay, get the idea that in when you plot the signal, you see it, no? When you plot the signal, you see it. Okay, plot the signal with some small value with n. Okay, so you can see that at 1, 2, 3, 4, 5, you will get the same value. Okay, so here if I put this n as 1, 2, 3, 4, 5, 6 likewise, I will get this value for both signal. Okay, but I don't know the reason why it not count. Okay, I can't understand. But I got the correct result when I tried it at so 2/5/3 by 2 to 5. So if you put 7, 5, let's see what happens. I don't know what is the reason. Okay. So anyway, I will figure out it and let you know. We will continue. Okay. Otherwise, now we are getting rid of time. one, two, X1, X2. Okay, if I plot using a subplot. But in subplot, you can see that the same result we get, no? Here, see 1, and here you will get 1, 0, 2, 0, 1, 0, 1. So you will get the same signal, no? Here, if you draw it here, likewise, no? You will get the same one. And here also you will get the same one like this. Okay. This value also should be same. Okay, but here it is not correctly shown actually. I think, I hope. So you can see that if I draw it, okay, if I draw it, so this, you see, this one and this red one and blue one look same, no? There is no difference. Okay, this value. What is this value? I couldn't understand. This 2 value is, at this 2, it should be 0, no? Okay, so anyway, you can see, just don't look at this value. Okay, look at this plot. Okay, so you can see that here the red one is cos 5 by 2n, and this is cos 5 by 2n. Okay, so you can see that both plots are same. Okay, there is no difference. Okay, so if we get the frequency, another frequency with the 25 number, 25 times the 25k. Okay, k can be 0 to 1, 0 to infinity, but it is an integer value. Okay, then you will get the same result. Okay, so you can see it in plot, you can see it. Okay, here at 2 it should be 0. I can't understand what is the reason here, but anyway, you will have the same result. Okay, here. Anyway, you can see the plots are same, no? So I think you got it. Okay, so I want to tell you that, I want to show you that this condition is satisfying when this n is integer value. Okay, so let's go, so keep those in mind. Okay, so let's move to the sampling. Okay, so if you want, get 5 minutes break and we will meet. Okay, so get the 5 minutes break and we will meet. Meanwhile, I will try to figure out the problem there. Okay, so get 5-minute break. So I am in my screen. Okay, I'm trying to figure out what is the problem. Okay, so you can stay with me. So we will start it. So we will start the session sampling again at 2:30. Okay. Okay, I hope you all back. Okay, so actually still I couldn't verify what is the problem. Okay, uh, so you can see it if we get 5/3. Okay, 5/3. Okay, 5/3, and the second signal will be 5/3 plus 2 5. 5/3 plus 2 5. That means 7 5/3. No, 7 5/3. Okay. So if you consider this signal 7 5/3, okay. So you can see that same value you get, no, for this array and this array, same value should get. We got same value, the identical value. Okay. In case of 5/2, also it should be same. Okay, but I will see what is the problem. Okay. But it happened. Maybe we have to ask Dr. Udesh. Okay. Because you can see that you you see that I think you can remember that. Okay, I think you can remember that. It is also mentioned that in case of continuous time signal, okay, the angular frequency that can be between minus infinity to plus infinity. Okay, and also the normal frequency also will be minus infinity to plus infinity. Okay, and you see that in discrete signal omega naught should be like between -5 to +5, and f, simple f. Okay, so here f is equal to 5, sorry, omega naught is equal to 5f, omega is equal to 5f naught or something. Okay, so using this identity we can get, here it is from -5 to -half to +half. Okay, this is in case of discrete signal, and this is in case of continuous signal. Okay, so it said that omega, we call this nominalized frequency. Okay, you call, we see that omega should be between -5 and +5, and f should be between -half and +half. Okay. So I get omega naught as 5/2. So it is a valid one, no? Omega naught can be 5/2. It is less than 5 and greater than -5. Less than +5 and greater than -5. So it should be, we should be able to use this. Okay. But unfortunately, we can't get the result. Okay. Anyway, I have checked it some different other value. I think you also can see it. If this is 5/5, also we will get the same result. Okay. Okay. So this will be 11 5 by 11 5/5. Okay. So also again you will get, so you can get, you can see that we get same result, no, identical values. So this should be true for half also, but I don't know what is the reason. Okay, anyway, let's go to the sampling. Okay, now actually now we are going to learn the sampling. Okay, now we are going to learn the sampling. So what is the sampling? Okay. So sampling is, we can say sampling is conversion. Okay, conversion of continuous time signal, or you can say analog signal, okay, into discrete time signal. Discrete time signal. Okay. So analog signal and digital signal, I think you have the idea what is analog signal and digital signal. So continuous time and discrete time, we divide based on the time value, no? Time values. Okay. If these time values are continuous, we call this continuous time. Time values are discrete, we set that discrete time. Okay. So analog and signal, I think you can remember that analog and signal, analog and digital, we divided with respect to levels. Okay. So if you have continuous level, we called it analog signal, and you have discrete, some finite level, you called it digital signal. Okay, digital signal. For example, okay, if you get this kind of signal, okay, up to here, let's say this is T, capital T or something. Okay, so you can see that here the time is continuous, no? From 0 to T, the all time values are there. So infinite values is here. Okay, so this is continuous time. And if you look at the levels, okay, so this is the amplitude. If you look at the amplitudes, you can see that there are, from here, let's say this is A or something, you can see that from 0 to A, all amplitude levels are there. Okay, all levels are there here, like this. So there are infinite level. So this is, we can say, we can call this is as continuous time analog signal. Continuous time analog signal. Okay. So if you get this type of signal, okay, so you can see that from here 0 to, let's say, T. Okay, so you can see that from 0 to T, all T values are there. All T values are there. Okay, all T values are there. But if you consider the levels, you can see that this is maybe A1, this is A2, this is A3, and this level is A4, and this level is A5. So you can see there are 1, 2, 3, 4, 5 levels. Okay, so here you can see only 5 levels. So this is a digital signal, but it is continuous time digital signal. Okay, digital signal. Okay, so in some books, I have seen that this type of signal also interpret as discrete time signal. Okay, but I don't know the reason why it say like that. Okay, but anyway, you can see that the time is continuous, but levels are finite. So levels are discrete actually. So if the levels are discrete, we can say it is a digital signal. Okay. So that is the, I just give a quick recap of analog and digital signal. Okay, take that idea. Okay, so in normal manner, if we have a discrete signal like this, okay, discrete signal like this, okay, sometimes this can be also viewed as a digital signal because we can count the levels. Okay, we can count the levels, number of levels. Okay, okay, but sometimes this is not a complete digital signal. Okay, this is not complete digital signal. Okay, so there is a process like quantizing. I think sometime you may have heard. So in future we will see this. Okay, after the quantization is done, this will be a complete digital signal. Okay. Okay. just I give idea. Okay, so anyway, any discrete signal sometimes we can view as a digital signal. Okay, that is what I want to tell you. Okay, but normally sometimes it is not considered like that. Okay, every discrete signals are not considered as digital signal. Okay, but in one side we can see it as a digital signal. Okay, okay, let's see what is the sampling. Okay, so sampling is a conversion of continuous time signal into a discrete time signal. Okay, so let's see, that is the sampling. Okay, so let's see, so if we have a signal like this, okay, so if we have a signal like this, okay, so this is a signal, and you can see that this is a continuous signal. Okay, so this is time. Okay, and this is the levels, frequency, sorry, amplitude. Okay, so this is the discrete sorry, continuous time signal. Okay, now you you send this signal through some kind of switch. Okay, you send this signal in some kind of switch. Okay, and at the output of the signal you are collecting the received signal. Okay, so now what you do is you on this switch for very small duration. Okay, so you have on this switch for very small duration. Okay, say for instance, okay, for instance you have switch it, then the signal pass through this switch, through this cable, and you will get some value here. Okay, then you off it. Okay, then you off it and you wait some time. Okay, then again you on this. Okay, then okay, then you will get another point there. No, you will get another point. Okay, so you will get another point like this. After that time, again you wait some time and switch. Okay, likewise you wait some time and switch the signal, and again wait something and switch the signal. Like this you switch and you just get this value. Okay, get this levels voltage. So if this is a voltage level, that means the voltage is varying with respect to time. Okay, so you see the voltage here. Okay, okay, so actually this is the sampling. Okay, so you can see that here we have this kind of signal, continuous signal, and now here as output of this switch. Okay, as output of this switch. Okay, this is the input. Okay, so input is a continuous signal, and output, as output we get some sample, no, sample or voltage value. If it is a voltage signal, some voltage value is there. Okay, like this. So this is a discrete signal, no. So by using this switch, what we have done, we have converted this signal into a discrete signal. Okay, if we tell it in another word, we can say we have collected some sample of this continuous signal, some sample. This is the first sample. If we from this side it is being sampled, no, from this side it is being sampled. So we can say this is the first sample, this is the second sample, third one, fourth one, fifth one, sixth one, seventh one, 8, 9, 10, 11, 12, 14, 15, likewise. We get some samples. Okay. So this is the sampling process actually. This is the sampling process. What we have done, we get the input signal, okay, continuous signal, this signal, and we collect some sample, okay. So here we have sampled signal. Here we have sample signal as output, okay. Or another word, we can say it is a discrete signal, okay. So if I we go further, okay, how this sampling can be achieved, okay, practically how this sampling can be achieved. If the signal is very small, very low time varying signal, okay, it is not the very high time varying signal, it is very slowly varying with time, okay. So it may be a voltage of a battery or something, say that is a voltage of a battery when connected through a load, okay. So it is reducing with time and it is slowly reducing, okay. So you can do like this, okay. So if you connect the signal source to some end, okay, say it is a battery, okay, battery or something, okay, say it is a battery. So this is battery, now is our voltage source, okay, and it is we have connected resistor with between the battery, okay. I get the example, okay, just the example, okay. So if this is a battery and this battery is connected to a resistor, okay. So you can see that some current will be flow through this resistor, okay, time with the time, and when this current is flowing through this voltage will be reduced, no. So this voltage will be reduced, okay. So we connect this through a switch to a multimeter, okay, multimeter like this, and we connect the other side, the multimeter ground to here, okay. So you know that this voltage is there, and this voltage with respect to time, it is solely discharging and come to zero like this, okay. So this kind of signal we can expect, okay, from this system, okay. And now what you have done is you just switch this for one time, okay, switch for one time and measure the voltage here, and you will get the voltage. And again you switch, you off the switch, okay, you open the switch, okay, and wait some time. Again you off on the switch, then some voltage will appear on this multimeter and you can mark that voltage. Likewise, after some time you can mark the voltage, okay. So after some time you will get zero voltage, okay. And this type of samples you will get, these are voltage samples, okay. So if this signal, if a signal is very slow signal, we can do that sampling in our hand, no, by our hand, okay. By our hand we can do the sampling, no issue. But for high speed system we can't do it with our hand, okay. We have to use another method, use electronic methods, no, okay. The another method is simple methods. You can try these things in your home if you can, if you interest, okay. So you can use a transistor, okay. So you can use a transistor like this, okay. So you can use this transistor as a switch, okay, okay, and you feed the signal here, okay. Then you send some voltage value to here, okay, to the base, okay. When you on this base, and base current will be there, and you will get this voltage here. No? At this point, you will get that voltage. Okay. So then you can off this base current. Then again on the base current. Then you can again see a voltage here, signal value here. Likewise, you can do the sampling using a transistor. Okay. So practical sampling can be achieved in many ways. Okay. The simplest form is using a transistor as a switch. Okay. Anyone can do it, but for high frequency sampling also, this method also not efficient, maybe not efficient. So we have to go for another electronically method, more advanced method using ICs, using high speed ICs and high speed electronic component, so on. So you can do the sampling very quickly and easily. Okay, so I hope you get the idea how the sampling can be achieved. We are not doing much thing. We just switch the signal with in time duration, with certain time duration, and get the sample. That is the sampling. Okay, so that is sampling. Okay, so another important parameters is there. That is this time, this holding time. Okay, the time. Okay, so if we get the sample signal, okay, so I said you that here we get the sample and stay some time and get another sample, and stay at some time and get another sample, stay some time, certain time, and get another sample, like this. Okay, so this time, what is this time? It is the time duration, this time, that is time duration between two successive sample, no? Two successive sample. Okay, so here one sample is there and another sample. Okay, so here t is the time duration between two successive sample. Okay, so we call this duration as sampling period. Okay, so keep remember, that is very important parameter. Okay, so that is sampling period. Okay, sampling period. Okay, so this is the sampling period, and this sampling period can be varied. Okay, so this t can be varied. That means you can collect a sample at some time, and then wait some time and collect another sample, and wait some time and collect another sample, and this time and this time can be this time duration, sample time, and this sampling period can be changed, different. T1 and T2 can be different. If this period is T1 and this period is T2, this can be different, no issue. Okay, but normally in our, actually most of practical sampling system, okay, this sampling duration kept as constant. So if the sampling duration is changing, it will be difficult to process the signal. Okay, difficult to do the analysis and also process the signal in electronically or something. Okay, so normally we kept this sampling period as a constant. Okay, so normally we kept this sampling period as a constant. Okay, so if the sampling period is constant, we called it uniform sampling. Okay, uniform sampling, another parameter. Okay, so again, I think you have a lecture at 3 o'clock now, so we will quickly wind up. Okay, and and this T, if you consider this T, it is a uniform sampling. If you consider this T, okay, if you consider this T, you can see that this so we read one sample. After T, we read another sample. Again, after T duration, we read another sample. Okay, so this T will get to read one sample. No, this is the time to read one sample. Okay, this is the time to read one sample, time to get one sample. Okay, so that is the sampling period. Okay, so if you want to find how many sample we read at 1 second, so you have simply divided it by T, and also this side also will be divided by T. Okay, so this is how many, 1 by T means how many sample we read at 1 second. Okay, for 1 second, how many sample we read? That is 1 by T, and we called it sampling rate, another parameter. Okay, sampling rate. So that is equal to 1 by T, and we normally denote it using Fs. So this is the sampling frequency. How many sample we get per 1 second? That is the sample frequency. Okay. So sampling period and sampling frequency are related to each other, and these are very important. Okay, so T is equal to 1 by Fs. This way also we can define. Okay, this is sampling period and this is sampling rate, Fs, or sampling frequency. Okay, and also it used as sampling rate. Okay, and in next week we will see the uniform sampling again. Okay, uniform sampling again. In sampling, you know that we convert xt, some continuous time signal, into a discrete time signal xn. Okay, okay, so normally if we have a signal xt, okay, if we consider our sampling period is ts, okay, ts, we get we get sample at every ts duration. Okay, for example, if xt is like this, okay, if xt is like this, okay, so we get one sample at 0. After ts, we get another sample. After another ts, so this is ts, this is 2 ts, we get another sample. And after another 3 ts, we get another sample. 4 ts, we get another sample. 5 ts, we get another sample. 6 ts, we get another sample, like this. Okay, so this is, we get the sample here. Okay, and we plot it with respect to n. Okay, n. So n is this number. Okay, so this is n at n is equal to 1 ts. This is at n is equal to 2 ts. This is n is equal to 3 ts, and 6 ts, like this, and it is n ts, like this. Okay, so if you plot with respect to n, you will get at 1 this, at 0 this kind of sample, at 1 this kind of sample, at 2 this kind of sample, at 3 this kind of sample, at 4 this kind of sample, at 5 this kind of sample, at 6 this kind of sample, so on. So you will get this kind of sample. Okay, so we convert xt into xn using this uniform sampling method. Okay, that means this ts is constant always. Okay, and this n can get value 1 or minus, sorry, plus or minus 1, plus or minus 2, so on, up to plus or minus infinity. Okay, from 0. Okay, likewise, so this n can be take such value. Okay, so we also can see that this xn is equal to, this is xt. Okay, so this is also in t domain, no? This ts, 2ts, 3ts are in t domain. So we can say this simple t is equal to nts. Okay, so in that method we can say this is equal to x in ts. Okay, here t is equal to n ts. Okay, so actually this is the sampling process represent in mathematics. Okay, this is the sampling process that is represent in mathematics. Okay, so you have to keep remember this point. Okay, xn equal to xnts. If you have xt signal, okay, then you will get the sampled xn. Okay, then xn is equal to x in ts, and here in ts equal to t. Okay, sorry, this is t. Okay, sorry, I'm sorry, this is t, xt, this is t. Okay, so likewise you can represent. Okay, so this is the mathematical representation of sampling, and this sampling period and sampling rates are also very important parameters. So next week we will see some further facts, and we will do some example. Okay, so I will try to figure out what is the problem there with my MATLAB problem, and I will let you know it. Okay, okay, and also, so we will wind up because you have a lecture, as I can remember, at 3 o'clock. Okay.